So units of measurement. Units are important. Let's look at this sentence. When my son was 7, he walked 3, and when he was 4, he threw his baseball 8 and said his school was 5 away. Does that make much sense? Not really. Units are important. Okay? When he was 7, 7 months, 7 years, 7 decades? No, probably not decades. He walked 3 steps, 3 blocks, 3 miles. I think, if I remember correctly, this is in the textbook. When my son was 7 months, he walked 3 steps. And when he was 4 years old, he threw his baseball 8 feet and said his school was 5 miles away. Something like that. That makes sense. But units are really, really important. If you go to McDonald's and you say, I'd like 2, what are you going to get? She's going to say, well, do you want a number 2? No, I want 2. 2 what? You want 2 Big Macs? 2 coffees? 2 hash browns? We don't know what you need. Units are really, really important. So I'm going to be on you about this all semester. If there is a unit involved with the number, write the unit every single time. You're going to need to show your work. And when you're showing your work, it's tempting to skip the unit and just write it at the end. Write the units every single time. That's part of the measurement. It's the number and the unit. So there's 2 common systems of units, the English system and the metric system. Scientists use the international system of units, which is also known as the SI system. And if it's the international system, why is it SI? Because it's from the French, and I'm not even going to try to pronounce that because I did not study French ever. The metric system and the SI system are almost identical. The differences between them are so slight that it just really does not matter for this class. So I'm going to treat them as interchangeable, having said that yes, they are slightly different, but the units and how the units work are the same. So these are basic quantities. Length, and for length, the meter is the unit. For mass, the kilogram. Time is second, that's the same. And temperature is Kelvin. And we're going to learn about those temperature units in Chapter 3. So let's look at these individual units. The meter is the standard unit of length. In the English system, we use inches and feet and miles and stuff. And in the metric system, we use the meter. The meter is defined in kind of a strange way. It used to be the length of this particular bar of a very inert metal, and it was stored in a very special place, I think in Paris. And they've redefined it. They redefined it in 1983. The meter is the distance that light travels in a vacuum in 1/299,792,458 parts of a second. What on earth? That's a really weird definition. Yeah, and I'm not going to quiz you on that at all. That makes sense to scientists, though. The advantage of a definition like that is that someone, let's say in Paraguay, could set up an apparatus and measure that. They don't have to travel to Paris and compare their meter stick to the official meter stick. Oh, let's stay here real quick. I would like you to have a clue about the sizes of these metric units. So a meter, 1 meter, the abbreviation is a lowercase m. This is in the ballpark of 1 yard. Okay, so a meter, roughly a yard. So about this long. It's actually 39 inches, and a yard is 36. What about mass? The unit of mass is the kilogram. And how is that defined? That is defined by this very special block of metal kept in France, and I'm not going to try to pronounce that city either. It's good to know roughly how big is a kilogram. A kilogram is about 2.2 pounds. So it's in the same ballpark as a pound. It's not a teeny mass, it's not big like a ton, roughly the same ballpark as a kilogram. The second, okay, we're all pretty familiar with the second. We know what a second is. How do they define a second? They use an atomic clock. Okay, so that's kind of interesting. There's a particular type of radiation emitted by cesium-133, and they record the duration of, 9 billion periods of that radiation, and that's a second. So they came up with this way. Because if you say, okay, this person's watch is the definition of the second, we're all going to base our definition on this. Well, you have that problem of having to have everybody looking at this watch. And then what if the watch breaks? What do? What if the watch slowly doesn't work as well anymore? Sometimes that happens with clocks. They don't keep time as well as they used to. Now everybody's definition of a second is wrong. That's not good. So they define it in this way, and not anybody could do this, but it's possible to set up something like this to measure in any country. So let's go back to the kilogram. Kilogram is a measure of mass. Mass is not the same as weight. Okay, we're familiar with talking about weight. You go on a diet and you're concerned about how much you weigh. Mass is the actual quantity of matter in an object, and weight is actually a measure of the gravitational pull on that matter. Weight is actually a force, whereas mass is a quantity of matter. So weight depends on gravity, mass does not depend on gravity. If you have a 1 kilogram object and you weigh it on a scale, with the English system it'll say 2.2 pounds, but it's still 1 kilogram of mass. If you take it to the moon and you measure its weight, the weight will be less because the moon is smaller and its gravitational pull is less. It's about 1/6 of the Earth. Has the amount of matter in that object changed by going to the moon? No. It's just that it's not as attracted to the moon because the moon has a lower gravitational pull. So mass and weight are intrinsically different. The good news is that as long as we don't leave this planet, we can kind of talk about them interchangeably. Anybody planning to leave this planet during the semester? I didn't think so. So you'll sometimes encounter the word weight or weigh. We'll say, go to the balance and weigh your sample and record its mass. So we'll kind of intermingle these terms, but I just want to be clear that they are different. So kilogram is the base unit in the SI system, but the gram is another common unit of mass. And the gram is we'll use grams a lot more than kilograms in chemistry because gram is smaller. We need to talk about prefix multipliers that are used in the metric system. So hopefully you have printed out that list of things I've told you to memorize. And on that list are some of the prefix multipliers. In the English system, when we need units of different sizes, we just have different units. So say you're measuring the length of my phone. What unit in the English system might you use? Do you measure it in miles? Inches. Inches would be good, right? If you're measuring the length of the room, you'd probably use feet or possibly yards. If you're measuring the distance between Tulare and Bakersfield, are you going to use inches? No, you'd use miles. And then we have relationships between those units, right? A foot is 12 inches. A yard is 3 feet or 36 inches. A mile is 5,280 feet. Those are kind of weird numbers, aren't they? Especially the 5,280. And those came about because we're using some units that are really, really old. I mean, a foot used to be defined as the length of the king's foot. So what happens when you get a king with little tiny feet? Does everybody have to change their measurements? I don't know. But it came about by these just funky ways of defining units. In the metric system, we have a base unit, like the gram or the meter, and when we need a larger unit, we just multiply it by factors of 10 so that it's roughly the size that we want. You want to measure things in a unit that's similar to the size that you're measuring. You don't want to use a unit that's way bigger. You know, my cell phone, you don't want to use a mile, really long unit to measure a little tiny thing. So you want to pick a unit that is similar in size or a little smaller than the quantity you're measuring. And we pick those units by choosing prefix multipliers to make the unit larger or smaller to fit what we need. So these are the prefix multipliers. They're all factors of 10. And the beautiful, beautiful thing about the metric system is that if you learn this one set of multipliers, these apply to all the units. The 12, 3, 5,280 in the English system only works for length. You go to weight and you've got 16 ounces in a pound, and you've got 2,000 pounds in a ton. You've got a whole different set of numbers. And then you get into the kitchen and there's 3 teaspoons and a tablespoon, and I can never remember how many tablespoons are in a cup. I cannot remember that one. But there's 2 cups in a pint and 2 pints in a quart and 4 quarts in a gallon. All these weird things to remember. This is beautiful. So how does this work? Okay, so these are the names of the prefixes, and there are other ones that we're not showing you, and I'm not even going to make you memorize all of these. It's on that list. But here's tera and giga and mega and kilo. And you've probably heard these in terms of bytes. Terabytes, gigabytes, megabytes, kilobytes. What is a byte? A byte is a measurement of, well, it's a certain number of bits. I forget how many bits is a byte. It's computers. A bit is one piece of information. Computers work in binary, and so it's either on or off. So that's a bit, and you put a bunch of bits together and you get a byte. But then, that's just like almost like one letter or something. And so then you put a whole bunch of those together and you need a larger unit. And so they've used these metric prefixes to measure computer memory. So a kilobyte, a megabyte, my computer's got a 1 terabyte hard drive. And it's just mind-boggling. It just can hold so much stuff. It's awesome. So mega has the symbol capital M. All of these prefixes have a 1-letter abbreviation. Mega is a capital M, and mega means 1 million. So you may have heard somebody, say, oh, well, that guy's getting megabucks. Well, what is a megabuck? A megabuck is $1 million. Mega means 1 million. So when you put mega in front of anything, it multiplies the size of that unit by 1 million. A kilo. Kilo means 1,000. You can put kilo in front of meter or gram. You could put it in front of any unit. You could put it in front of feet and say kilofeet. And people look at you funny, like you're mixing your systems. But you could, and we would understand what you mean. Kilo means 1,000. So a kilogram is 1,000 times larger than a gram. A kilometer is 1,000 times larger than a meter. A kiloliter is 1,000 times larger than a liter. So we use kilo a lot in chemistry. We don't use deci very much. We do use centi. Centi means 1/100th. How many cents are in a dollar? 100. How many years are in a century? 100. Okay. A centimeter is 1/100th of a meter, just like a year is 1/100th of a century. So centi means 1/100th. So here are the multipliers expressed in decimal form, and here they are expressed as powers of 10. For some of them, like kilo, a lot of people find that 1,000 is easier. But when you get to things like nano, I don't feel like counting out 8 zeros. That's annoying. And you get to these guys, pico and femto, those won't fit on your calculator. And so these exponents, these powers of 10, I think is the best way to remember the values of these different units. Kilo is 10 to the third, centi is 10 to the minus 2, milli is 10 to the minus 3. Question?
On our quiz, do you want us to know both, or could we know like the power instead of?
That's a good question. On the memorization quiz, do you need to know both, or could you just know the powers of 10? I would say that you need to know the power of 10. If you want to learn the other one, that's fine. But you need to know the power of 10. Okay. So all of these guys here, tera is a capital T, giga is a capital G, mega is a capital M. So they're starting with the initial letter. We run into a little bit of a problem here, though, because milli and mega both start with M. But mega makes it bigger, so mega is a big M. Milli makes it smaller, milli is a small m. And then we have micro, and we have run out of English M's. So we turn to the Greek alphabet. And this funny little guy here is the Greek letter mu. That's the Greek version of an M. I know it doesn't look like an M at all. It looks like a U with a funny tail at the beginning. But you do need to know this guy because we do use this in chemistry quite a bit. Micro, it's a mu, this funny little guy, and that means 1/1,000,000th of whatever unit you're talking about. And you do sometimes see micrograms like on vitamins or something. You know, you get a vitamin or a supplement and it'll be 10 micrograms. Now sometimes they abbreviate it incorrectly and they abbreviate it MC grams. I don't know if they can't come up with a micro symbol or the mu or what their issue is, but they do that sometimes. So you need to know the ones that are on the list, and you just need to memorize them, okay? That'll make things a lot easier. So here's just an example of choosing units. A short chemical bond is about 1.2 times 10 to the minus 9th meters. What prefix multiplier on meter should you use to make it an appropriate unit? Nano. We want to use nanometer for this because a nanometer is 10 to the minus 9th meters. Nano and 9 kind of sound alike. That helps you remember. You want to use a nanometer because now you've got this down to the scale of what you're measuring. So that chemical bond in nanometers is going to be 1.2 nanometers instead of this little teeny tiny number. Any questions? Yes? Could I give another example? Sure. So let's say we're going to measure something that is 2,750 meters long. What would be a good unit to use? Kilometers. Okay, because this is in the thousands. Kilometer is 1,000, 10 to the 3 meters. So then in kilometers, that's going to be 2.75 kilometers. Does that help? This example is not something that we're going to see problems on or things that I'm going to test you on. This is more of an example of just thinking about how we like the unit to be similar in size and how we can use the multipliers to change the size of the unit to make it appropriate. So we went over the base units, the meter, the gram or kilogram, and second. Those are our basic units. Then there are also some derived units. These units are derived from other units. And there are other base units, but we don't deal with them in chemistry, and we're not going to talk about temperature right now. So derived units come from other units. Units of volume are actually derived. Many units of volume are derived units. How do you find the volume of a block of wood? It's the length times the width times the height, right? So that's one of those geometry equations. Volume equals length times width times height. Well, if you measured each of those in meters, what would your volume unit be? It would be meters cubed. Meters times meters times meters. So if you measure those in meters, you're going to end up with meters cubed. If you measured it in inches, you'd end up with inches cubed. So cubic meters, cubic centimeters, cubic millimeters are all units of volume, but those are derived units because they come from meters, centimeters, millimeters. The unit of volume that is not a derived unit is the liter. And its common variation that we see is milliliter. Do you remember what milli means? 1/1000th. So is a milliliter bigger or smaller than a liter? It's smaller. A milliliter is a little bit. Do we have a clue about how big a liter is? I know what 2 liters looks like, right? 2-liter bottle of soda. 1 liter would be half of that. So it's helpful to have a clue about how big these things are. That's the end of that section.